So in the last session, we discussed about the design of two-way simply supported slab, and we completed up to the reinforcement detailing. In this session, we'll be seeing the checks that are required for a two-way slab. As we have already completed the checks that were required for one-way slab, this will be our final portion of the checks, and the remaining part, that is of two-way simply supported slab, which will be of supports that are restrained, or you can say supports are held down, will be our next topic. And then we'll be moving towards our final topic of this chapter, and that will be a two-way continuous slab. So for regarding purposes of check or for checking the conditions, this will be our final session regarding checks, because in later sessions also the checks will be the same that we are going to see now. So moving on to the question. So the question here is the same that we have discussed in the previous session. The only thing that we are doing is providing the checks. So the first check of ours will be check for cracking, and for check for cracking we'll be always looking towards our page number 46 of IS code, and in that we will be looking towards our clause, that is 26.3.3, and the category slabs. Now keep in mind, in both the directions we have provided main steel, so there is no consideration of distribution steel in this topic. So in X direction, that is our shorter span, and Y direction, that is a longer span, in both the cases we will be checking only this first parameter regarding our check for cracking. So moving further, first we will be checking about the LX axis. So the both conditions, that is condition number 1 and 2, will be the same. As you can see here, the first condition is it should not be more than 3 times the effective depth. Now as we are dealing with the X axis, the dx, that is depth or effective depth along X axis, was 110 mm. So in this case we will be substituting the value 3 into 110, that comes out to be 330, and in later portion it is prescribed or 300 mm, whichever is smaller. So out of these two cases, as we all know, the 300 mm will be the smaller value, and 190 was the spacing that we have provided. So our provided spacing is less than 300, so our answer is satisfied. Okay. Now the next thing, that is along y-axis. So along y-axis also the answers will be the same, that you can see here. Along y-axis the checks will be pertaining again to this topic only, that is our main steel. So conditions will be the same. First condition will be 3 times the depth of slab, that is effective depth, and along y-axis our depth was dy, which we have supposed or assumed to be 100 mm. So our condition comes out to be 300, that is 3 into 100, and the second condition is 300. So out of this both cases the smaller value will be 300. So the spacing that we have provided in y-axis or along ly was 200 mm in the previous session. So as you can say that 200 is less than the maximum allowable spacing, that is 300. So our answer is satisfied and it will not fail under cracking. Moving on to the second check. The second check is check for deflection. Now keep in mind here we will not be dealing with both the axes. This is the only change that we are dealing with our one-way slab and two-way slabs. In one-way slabs we are always checking along the main steel part, that was the shorter span. But in two-way slabs certain checks will be requiring the checks to be performed under shorter span, whereas certain checks will be requiring checks to perform under a longer span. So this is the basic difference between a one-way check and a two-way check. So in the first case, that was check for cracking, we need to check along the both the axes, that is along X direction and along Y direction. But for check for deflection we will always check along the shorter span. So keep in mind, no need to check along ly, we will be always checking along lx only. Okay, so you need to keep this in mind while solving in your examination. And as we all know, the checks will be identified from this that we have obtained from page number 39, and the criteria again will be the same, just rectifying the criteria. There were two limitations to use these ratios. The first limitation was the shorter span should be less than 3.5 meter, that is less than or equal to 3.5 meter, and the live load should be less than or equal to 3 kilonewton per meter square. If both the limitations are satisfied, then and then only we will be using this ratio. In our sum, both the conditions are satisfied, so we will be using this ratio from page number 39 of your IS code. So as you can see, for simply supported slab, the ratio was 35 into mf. But again, keep in mind the last parameter or the last statement is very important. For HYSD or FE 415 bars, the equation or the ratio will be multiplied by 0.8. So our equation comes out to be allowable L by D equal to 35 into mf into 0.8. Clear? Now this allowable L by D, it's, you can either substitute here capital D or you can substitute small d, as we have discussed previously. It is no concern. So moving further, the first thing that we need to find is the PT, because we will be referring it to the figure number 4. So PT, the equation will be 100 AST by BD. So we will be using these 3 pages. Page number 37 will be used when the ratios or the limitations are not satisfied from page number 39. So for two-way slabs, we will be first moving on to page number 39, and then only we will be moving to page number 37 if our conditions are not satisfied. And page number 38, that is our figure number 4, we will be considering it in any scenarios. So these 3 pages are important regarding our check for deflection. So solving it, the PT comes out to be 0.24. Clear? This was our AST provided. This AST will be the AST provided that we have done. So the PT comes out to be 0.24. So moving further, the next thing will be to find the MF, that is modification factor. And as we know, the PT content is 0.24, so it will be somewhere around here. And FS, you can solve by this equation, that is 0.58 FI, that is 415. AST required upon AST provided. So by solving this equation, we are getting the value of MF to be around 2. If you are getting an answer to be 1.7 or 2.3, it is well and good. The range is not specified. The answer may vary according to the decimals that you have taken. So from my understanding, the answer comes out to be 2. So next step will be to find the allowable L by D. So our allowable L by D will be 35 into MF, that is 2, multiplied by 0.8, which comes out to be 56. Now the next step will be to find the actual L by D. So our actual L by D will be L upon D, that is Lx upon dx. So in this case, Lx is 3110 and dx is 110. So the value comes out to be 28.27. So this is the actual L by D that is occurring in our slab, and the maximum allowable L by D is 56, which is greater than the actual phenomenon. So our case is satisfied. So this was our check number 2, that is check for deflection. Now moving on to the third check. The third check will be check for development length. Again, the development length should always be checked for the longer direction. So again, revising all the 3 cases. The first case was check for cracking. Check for cracking is to be used or to be solved for both the axes. Second was check for deflection. Check for deflection will always be solved for the shortest span. And third will be the check for development length, and check for development length will be solving for the longer span. Okay, so moving further, the equation that we'll be using is LD, that is development length should be less than or equal to 1 or 1.3 m1 by d plus L0. From the page number 44 we will be getting it. We'll be using page number 44 and 42 in this check. So first, moving on to page number 44, this will be the equation that we are using, and this will be the condition that we'll be using to value or to multiply the value by 1.3. So the first thing that we'll be calculating here is L0. L0 is sum of anchorage length. So as you can see here, L0 is mentioned as it is limited to effective depth or 12.5. So effective depth, as we have considered the longer span, so or the longer direction, so longer span, that means Ly. So the effective depth will be considering will be dy. So first case will be 100 mm. Second, the case is mentioned as 12 into 5. So 12 into 5, that means 12 into 8. Some of you might have taken the value to be 10. No, there is no issue. So the answer comes up to be 96. So the statement that we have given is the value to be considered is the greater of these both values. So out of these 2 cases, the greater value is 100. So L0 in our case will be 100 mm. Okay? So the first condition is satisfied. Now moving on to the second condition, we will be needing to find the shear force. So to find the shear force or to find the bending moment, the next step will be to find the AST, that is steel content, as we are dealing with development. Now keep in mind, the maximum bending moment will be occurring in the center of the span, that is center of the slab, whereas the shear force will be occurring maximum at the supports. So we have calculated the AST in the center of the span, that is along LY direction. So for calculation of the supports or calculation of steel at the supports, you always need to assume the 50% content of the steel that is provided in midspan. So AST at supports will always be 50% of that provided at the midspan. So in this case, AST at supports comes out to be 125.5 mm square. Clear? So now moving on to the next thing, that is to find the shear force. So shear force, as you all know, it is a simply supported slab. So our equation will be WL by 2. W, which was our load, total load that we calculated in the step number 3, and the LX, that will be my 3.11. Now why LX? Because we are always considering the perpendicular distance. Keep in mind, as we are dealing with the longer direction, that means we are taking y-axis. So the perpendicular direction to y-axis will be our x length. Clear? So here we will be always substituting LX. Now some of the students are always make mistake in this case, that is, if we are considering the longer direction, then in hurry they are placing the value Ly here. But keep in mind, this is the axis there that we are considering. If we are talking about the y-axis, the direction or the distances will always be perpendicular, that is Lx in this case. Clear? So equation will be substituting is W into Lx divided by 2, and the answer comes out to be 17.2 kilonewton. Now the third thing that is remaining is the moment of resistance, that is M1. So in every case of slab, whether it will be a one-way slab or a two-way slab, we will be always assuming our slab to be under reinforced, that is XU is less than XU max. So from page number 96, you can see here we will be always substituting this equation to find the value of M1. So here the AST that we have calculated earlier, which will be at supports. Clear? So 125.5, and the answer comes out to be 4.41 kilonewton into meter, or into 10⁶. That will be in Newton into mm. Clear? So we have completed all the things that we have required to find the RHS portion. So now we'll be substituting the value of RHS, that is 1.3 m1 by V plus L0, and the answer comes out to be 433.33 mm. So now we'll be moving forward to the LHS portion, and the LHS portion is LD, that is development length. And for that we'll be moving to page number 42 of our IS code, and from page number 42 we'll be using this equation, that is LD equal to phi sigma S upon 4 tau BD. Phi, that is the diameter of bar, we have assumed to be 8 mm diameter. If you are assumed it to be 10 mm, then place the value to be 10. Sigma S will be 0.87 into Fy. Fy in this case is 415. So answer comes out to be 361.05 Newton per mm square. We have given M20 concrete and Fu415 steel, and we have taken 8 mm bar, that is in tension. So tau BD comes out to be 1.92 Newton per mm square in this case. That will be getting from the table mentioned in page number 43. So solving it, we are getting LD, that is our LHS portion, to be 376 mm. Clear? So our final check was that LHS should always be either less than or equal to the RHS portion. So LHS value comes out to be 376, whereas RHS value was 433.33. So our condition is satisfied, and the third check is completed. Now moving on to the fourth and final check. The final check will be check for shear. Clear? And now keep in mind, check for shear again will be for longer span. Clear? So again revising everything, first was our check for cracking, which will be dealing with both the axes or both the directions. Second was check for deflection, that will be checking for only shorter span. The third and fourth check, that is the third check was check for development length, and the fourth check, that is check for shear, will be always dealing with the longer span. So keep in mind in these cases while you are solving your examination problem. So now the first thing will be to find the shear force that we have already calculated. The answer that comes out to be was 17.2 kilonewton. And the next thing will be to find tau v, and tau v will be getting from page number 72 of your IS code, and the equation is tau v equal to Vu by Bd. So Vu, that is our shear force, D will be our width. We will be always taking the width to be 1 meter, that is per meter analysis, and D will be 100. Why 100? Because we are dealing with the longer length or longer span. Clear? So D comes out to be 100 in this case. So our answer is 0.172 Newton per mm square. So our LHS portion is completed. In the fourth check, we always need to find that tau v is less than tau c dash. Clear? So now the second step will be to find the tau c, but for that we will be first needing to find the value of pt. So pt, that is 100 ast by bd. Ast again will be substituting for the longer span, that is ly. That comes out to be 0.251 percentage. And now from the value of pt, we will be solving the value of tau c from page number 73 of your table. If you are not getting a correct answer, then do interpolation to get the perfect answer. Tau c comes out to be 0.36 Newton per mm square. So tau c is completed. Now we'll be checking tau c dash, and tau c dash will be equal to k into tau c. So the next step will be to find the value of k, that is our constant, and for that we'll be solving this clause, that is 40.2.1.1 on your page 72. Clear? Now our overall depth will always be less than 150 in the case of two-way slab. So for two-way slabs, our k, that is constant value, will always be 1.3. So the k value will be 1.3. Now substituting the value of tau c dash. So tau c dash will be k into tau c, which comes out to be 0.468. So the ultimate goal was to find or to prove that tau v is less than tau c dash, which here by is confirmed. Yeah. So these were our checks. We will be not entertaining the checks in the later portion. So please solve this, and this was the design problem that we have concluded, or you have solved it, and the further checks are to be required, as this is the last portion of checks that we will be dealing with. Okay. So in the next lecture, we will be dealing with the problems pertaining to corners are held down situation. Thank you.